Je vais vous demander de faire un petit peu de silence pour le premier talk technique de la journée. Donc, let the plants do the talking. Estimate smart agriculture by the message received from plants and soil par le distinguished lecture de la Circuit and System Society et professeur à l'Université Polytechnique de Turin, le professeur Danilo Demarchi.
Merci bien. Bonjour à tous. Bien, je suis très content d'être invité ici. Je suis très heureux de partager avec vous qu'est-ce qu'on fait à Turin, qu'est-ce que je fais dans mon groupe. On a parlé du futur. Je pense que les anciens comme moi peuvent vous donner un petit peu des idées pour le futur. Mais maintenant, je dois passer à l'anglais parce que je ne suis pas prêt à faire la présentation en français. Vous voyez, je parle un petit peu français, mais pas beaucoup pour faire ma présentation. So let's switch to English. Well, as was introduced, my presentation is a CAS Distinguished Lecture. So this means that I was invited by Circuit and System Society to go around the world, and I'm happy to be here in Bordeaux with the good friends around here. For showing you, sorry, I have maybe to switch off my microphone. Wait, as I listen back. Okay, yes, okay. Okay, sorry, I had an echo. Well, to present you the brand new topic and applying our technologies, electronic technologies, to agriculture. I consider it a new, even if, of course, nowadays in agriculture already there are a lot of electronic technologies, but nowadays I hope that I will be able to share with you that we are in front of a new start, because we have really new possibilities with our technologies to be engaged inside this topic. Well, I am inside, I'm leading in Torino, the group, we call it eLions, so electronics, life-oriented, intelligent system, so life-oriented. In fact, I'm coming from biomedical engineering. I was teaching for years electronics for biomedical engineering, but because we are talking of living systems, I will hope demonstrate you that, of course, you already know it, but the plants are living systems. So to move from biomedical engineering to plants, it is a sort of straightforward step. What I will share with you today, I will start from the roots. I will start showing you the basic concepts that are taken from where we take inspirations for applying our technologies and apply our strategy to obtain the results, and so to collect the fruits of our work. And I will go inside with some examples. Okay, let's start from the roots. I want to share with you some concepts that are started recently to be introduced by the World Bank Group, the FAO, and also from the World Economic Forum. Here, what I like very much, and I will talk about firstly the impact that agriculture has on climate change. All what we are talking about, it is strictly related to climate change, to sustainability, because last year I did a talk with one fantastic friend. He had a PhD degree here, Victor Greenblatt from Chile. You know him by sure very well. So with Victor, I did a talk titled how agriculture is impacting climate change and how climate change is impacting agriculture. So it is a topic in which it's important to work also in terms of impact of climate change, because sadly agriculture, it is charging the percentage of greenhouse gases of about 20%. So it's a lot. So we have to work on it firstly. And from the other side, but it's important to have agriculture, as we don't eat anymore. So it's a must. The population is increasing. So this is why let's be a little bit superb, guys, to say we, electronics guys, we can be helpful in it. And I hope to show you why and where. Well, of course, I will not touch the importance of wasting food, but of course, we can do something, we can do some actions for maybe following and monitoring food, okay, during its value chain, but in particular, I will talk of production, okay, of side. What I really like, a term that was introduced because I told you the importance of the contact with climate, it is this term that says not just smart or precision agriculture, but climate smart agriculture. So we need to be linked always to the concept to be sustainable, and what I want to highlight immediately, sustainability is important, is fundamental for the environment, but we have to go in parallel with economic sustainability. So we need both. And again, electronics can be helpful in it, and we will see why. Because we have to, of course, increase productivity. People around the world are growing, so it is a must. And from the other side, we have to enhance resilience. Already, of course, crops are resilient by nature, but they need an help because the climate changes are changing the way that maybe farmers have to get decisions. And we can give to the farmers objective information. So from where we can help them. What I want to highlight immediately also is the fact we, with our technology, we will not replace the job of farmers. We have to cooperate strictly. It is a joint work because we are not experts. They are experts. I will discover, and I discover every day, plenty of interesting things. So it's a joint work. And from the other side, we can reduce emissions. As I said, we can work in reducing our emissions, and also we can, it's not written here, optimize the resources. I will show you an example how to optimize the use of water, but we can talk of pesticides, we can talk of nutrients. So thanks to our job, our work, we can help really to optimize what is done in agriculture. Well, I want to show you this video that it was from the World Economic Forum, that you see, I'm very proud of it, that the first technology that they say will change the future is exactly what we are talking about today. So here they mention wearable plant. I just published last year, the end of last year, a paper titled Wearable Plants. Because as I said, I'm arriving from biomedical engineering. And I always say, I was doing wearable for humans, now I do wearable for plants. In terms of electronics are very similar. There are very similar things. So, from the other side, it's a new topic, but we don't have to reinvent the wheel. We will have to be careful of some aspect that I will highlight later. So, starting from, I hope, all these concepts that I hope that I a little bit convince you that maybe is an interesting topic, let's go to see also in some details in this publication done by FAO, in which at the end, in the conclusions, there are some interesting topics. that I want to a little bit go in details. One important thing, agriculture, when you have to monitor a crop, when you have to monitor something, maybe you have to monitor animals, in this case it's talking of crops, site specific. So a field is different inside the field itself. So the soil is not equal everywhere. Here we are in a fantastic place for wine production. So wine production, you do it in hills often. So the hill, you have the water is not equal distributed everywhere. So first of all, second, also the content, the composition of the soil can change in the same crop. So imagine talking about different places in the world. So here, electronics is a key because we are flexible by definition. We can program electronics. We can change real time the behavior of our circuits. So this is one of the important points. And from the other side, remember, site-specific, so means in the same crop I have several places different in the same crop. So I also need a high number of sensors to be effective. Second, of course, here, of course, FAO also highlights the importance of the cooperation that we need from the local and national institution. And another, the last important topic I want to mention here, highlighted by FAO, is implementing practices at field level, where we can call it the knowledge of what we can do is very poor. People are not understanding how we can be useful. The farmers, I tell you, nowadays are very skeptic in our job. So one of the important things is to demonstrate that we are able to do something. But we are able to do something also if we listen them, we understand what to do, and we do it and we demonstrate. So in this case, FAO is setting up all around the world specific sites in which they demonstrate the use of technology, and so for convincing the people that the new technologies can be helpful. So, moving to more technical details, now let's see what is climate smart agriculture. Probably you already have some basic concepts about it, but climate smart agriculture means to be inside the crop. So to go to get information from the crop, from the soil, from the weather, so the environmental, and also to get the information. You can get information using satellites, you can get information, drones are a very nowadays important and effective way of getting information. And after all this data have to be sent to a central control, to a decision support place where you have your system getting the information, processing them, and so on. What I want to highlight here, one point that is important is also that directly on field is important to do some processing. Edge, okay, on the edge, in the fog is important, because you know that the local elaboration can help you, the local processes, in avoiding to send out data. You know that when you transmit is when you consume more. And I will highlight many times after the fact that in the crop, in agriculture, we must be low power. We cannot think to spread batteries in a field. So we have to think about it seriously. So, and then everything that is elaborated has to be communicated to our end users in an easy way. So, to giving them the possibility to take the right decisions. So, what I say, we can do this in 3 different implementation steps. We have a first layer in which we go inside the field, inside the crop. And here we are talking of putting sensors in the leaves, in the twigs, in the branches, everywhere, and those goes in the soil, in the air, in water. What the farmers tell me about it is that plant, soil, environment are a unique system. You cannot think about them separately. So you have to really go everywhere to get your information. And in this case, you can have information about the health status of your plant, of your soil, to detect the use of pesticides, the presence of parasites, and so on. And then you have to move up and say, okay, I have the data. I have to distribute the data around the crop. So to set up what we can call a plant area network or an internet of plants is named also. Because, and I will show you, the plants already talk each other. I read a very good book of one of the Italian colleagues from Pisa, Mancuso, and there was an experiment that demonstrated that the plants talk each other. When one plant in a corner of a forest has a problem, after, okay, in agriculture, in plants, real time means minutes or hours or days, okay? So, after maybe hours of days, the plant in the other corner of the forest activate the countermeasures to the problem, even if it doesn't have a problem. So the plant receives the message, be careful. So the plant sends to the friends, the other plants, the communication. So they are interconnected. They are interconnected, they say, along the soil with some microbes or some fungi, or also by volatile compounds, and I will touch them later. So, one way is, and so I took the idea from Mancuso saying, we can interconnect now. Let's see. And I will show you how we can do it. Because again, locally, I can already do things immediately. And after, of course, I have to send out the data. I have to send out the data to the cloud, to process them, and to obtain the information that I need to give it to the farmers, to the end users, for helping them get the good decisions, of course, as soon as I can, as much as I can, also to automatize the decisions. But everything cannot be done in an automatic way. Of course, I need the help of the farmers. Just to now summarize what I just mentioned, which are the main goals. So, we want to be sustainable for optimizing nutrients, resources, first of all, water, of course, chemical treatments and pesticides, informing our stakeholders with alarms, warnings. And this is what I say always. In this distinguished lecture I'm doing. We can be today able to do it. People are asking me, you are working on biomedical engineering, so in biomedical engineering there are already a lot of technologies applied to humans. Why we did not do this in agriculture before? We did not do it because technologies were not ready. Because now we can think to flexible electronics, to biocompatible, to biodegradable electronics. We can start thinking to low power, very low power, to power our devices without batteries. So now is, in my opinion, a good time to apply this. Because we want to detect the plant health, transfer information is already said, but what is important is that at the end we reach good food safety and good quality. Okay, so which is the strategy that I'm suggesting, and I'm very proud of it, that the World Economic Forum said it is the future, okay? I've started to work on it a few years ago, as you can imagine. How we feed the roots, how we feed the concept that we just mentioned. Of course, now I guess it's clear, we want to spread all around the crop sensors. We want to exchange information in the crop, to let the possibility to the plants, to the places, to the soil, to, apply. I don't know if you are young, maybe you don't know too much Aerosmith, but I get this title, they sing, let the music do the talking, I say, let the plants do the talking. So this is the idea from where I took the title of my presentation. So, how we can give word to the plants? First, application driven. So, please, if you work on it, you don't have to be technology driven. I learned a fantastic lesson when I was a PhD like you, when I went to an hospital, working on biomedical engineering, and the medical doctor told me, engineer, don't invent a problem for solving by yourself. This is the way of engineering. No, listen to me. I know the progress, and this is the point. Okay, of course, I exaggerated the concept. Hopefully, we don't behave like this always, but sometimes we do it. We know. So, please listen the end users and think to conceive the solution for the application. It's the application that asks you what you have to do. So you must understand which data to collect. We, in particular scientists, we would like to have everything, all the possible data, all maximum accuracy. Probably is not needed always, so be careful. We need a feedback to say to the farmers what they need, not just the information that we have a precision of the 1%. They don't care. They want to know if the plant is good or not, if they will have a good harvest, okay? And then the necessary countermeasures, also what you have to do to solve the problems. So what you have to do? Multidisciplinarity in this case is fundamental, because of course, we are talking of electronics, but for applying the right electronics, we have to understand agronomy, chemistry, biology, so we have to interact with all these colleagues. So, putting our sensor in the plants, which are the most important technologies that I see can be really the change, okay, of paradigm. Flexible electronics. The plant is a living system, so I cannot put PCB boards on the top of, or inserting PCB boards inside the plant, okay? So flexible electronics are a key. Transparent. On a leaf, I cannot put a sensor on a leaf that is not transparent, else the leaf, sooner in a few days, will die. Self-powered, I mentioned already, this is fundamental. We have to think. So always, what is now the situation? Which is now the situation? Me, electronics designer, I'm consuming this. The energy harvesters are giving me this power. So we have to we have to decrease how much we are consuming, and the colleagues working on energy harvesting have to decrease the efficiency of production. But we are really close. I will show you a real example of it. So we need, by sure, smart electronics. And what I said, flexibility in terms of electronics decision. And in this case, intelligence, artificial intelligence, I always say, before we need human intelligence. If we do a good application of human intelligence, we can really design fantastic artificial intelligence systems, because it's again another way of applying the right way technology. So we have to communicate to the cloud, and this last word sentence, user-friendly interfaces. We cannot think something too complex, else will not be used by people. what is differentiating what we are doing in agriculture from biomedical applications. This is the last reason why now agriculture is a field before it was not. It is that we must be low power, I already mentioned it, and low cost. Imagine, for monitoring a human who is having problems, so the guy spends every money for having a good pacemaker for saving his life. It's not a matter of money, just for saving his life. You cannot think to a farmer to put the same cost of a pacemaker on an apple tree. It's not convenient. So, low cost and low power are the two drivers application really. The two drivers that are giving you the right guide for setting up interesting solution. So, after this, I hope enough detailed introduction of what we can do, I want to go to collect the fruits, and so to show you some examples of applications. I start, of course, from the data. The first thing that we have to do is collect the data. We need data. For having the data, we have a sort of business as usual, what is already done today. So, to use visual, videos, cameras, and electro or chemical or electrochemical sensors. About visual, let's see, for example, people are getting images for understanding the health of a crop, of the soil. You know, you see you have some bugs in your tree. So, visually speaking, and you can obtain, you see, also by using machine learning, 90%, 95% of accuracy, you measure not just RGB, but also near infrared, so multispectral cameras are used. But I always say, when I want, again, let's go to an example in biomedics. I want to understand if a person is not healthy, I can look to the person. Probably he's sweating, he's white. So I see it's not good. So I know he's not in a good health. But what do I do immediately? I immediately get at least a thermometer. I get some electrodes for measuring the ECG. So I go in place. I go on the body of the person to understand the problem. Here, the concept is the same. The visual, video, photos, satellite images are very important. Again, we don't have to replace them. We have to add other information to this information, okay? So, nowadays, people, for example, here, I listened also a presentation of University of Reims working on images for the champagne production, you know, better than me, Reims, they are famous for it. For detecting the ripening of the fruits and everything. But one very important and very challenging thing is to measure what are named volatile organic compounds. Because this is exactly one of the ways how the plants tell us how they feel. Because they emit ethylene, methyljasmonate. I just put down some examples that are gases. They emit, for example, ethylene where they have problems. And they communicate, people, of course, this research is absolutely open, they could maybe communicate also each other, as I was mentioning you before. People are more convinced that they're using fungi in the soil, but I can say that these volatile organic compounds are very of great interest. And we are challenging because, you know, to measure, to do an electrochemical sensor, it is challenging in terms of stability, robustness, and also selectivity. They are very, very challenging, but they are very important. So this is one of the open fields for research to also design. Nowadays there are fantastic sensors for gases, for oxygen, but they cost a fortune. Talking of the field, fortune means 50 euros. 50 euros per sensor, forget, but it is useful for agriculture. Because I learned that usually, probably for 1 hectare, we need from 5 to 10 places, different nodes, different places for getting the result. So you can imagine, you cannot think to spread around a crop of few hectares, main sensors that are needed for the job. So this is another challenge, and in terms of elements, nitrogen, phosphorus, potassium, what is NPK is another challenging way for technology to reach the target of agriculture, and also is important evapotranspiration. So in this case, how the plant breathes. Okay, so you can measure, and again, there are very nice and important and very efficient now sensors, but they cost a fortune. So people are putting a lot of this in researching it. But so, as electrical engineers, we said, but wait, listen, maybe can we have a easiest, cheapest way of measuring our parameters inside the plant? Tomorrow I see you have a presentation about bioimpedance. Bioimpedance, living system. Also the plants have a bioimpedance change, and they tell us things. So this is why we started working on impedance sensors, okay, in the plant. And here you see, this is one of the first example that the first plants that we started to put in our labs. We are working on tobacco. Well, I just tell you a nice story. We work on tobacco. I don't smoke, okay, so it's not a personal interest. Because I started working with this, probably you have seen, I've been 3 years visiting professor in Tel Aviv University, and in Tel Aviv we decided to share the same plants for working, and also, you know, plant tobacco and the other plant I will tell you are good plants, but not so large, so I can do my experiments, electrical experiments on the plant after. Now I will show you, we have of course experiments in the field, in the crops and everything, but from Tel Aviv they told me there are 2 plants that are very well known because we know everything, all the sequence of DNA, they are tobacco and marijuana. And I say, okay, but if I come back to my director, okay, to you and say, I want to put a probably yes, the answer will be no. So I said, okay, let's go with tobacco. So this is why we are working with tobacco. And we don't smoke after, because we kill them, I will show you. But anyhow, just out of this job. Tobacco is perfect because it has the same behavior of apple, kiwis, other plants in terms of bioimpedance, so it's perfect for doing our study in our labs and after to move, of course, outside. And exactly the study of the impedance, after I will show you some other details of it, the study of the impedance is, you see here, this is what is a standard measurement, that is the soil water potential. Because it's not enough to measure humidity of the soil. Soil water potential, I learned from agronomists, is how the plant is able to get the water. This depends on the soil, how the soil is made. And depends on the quantity, of course, of water, but it's not enough a quantity. Maybe you can have water, but the plant is not able to get the water. So the soil water potential, it measures exactly this. And then you see here on June 9, in 21, we water the plant, and you see here that, of course, the soil water potential 0 means we are completely watered. The impedance, the modulus of impedance, you see the average of the modulus of impedance goes down. Clearly, means okay. In fact, one of the first studies we did is water stress of a plant. As you can imagine, the plant lives because of water first. So to measure the water stress, it's the first important, like to us, to measure if we have our heart that is beating. It's almost a similar thing. You see here, this is the average, but you see here periodical changes in modulus and also in the phase. We will talk more about the impedance. These periodical changes, I will show you later what they are. But the first thing is, what I want to highlight you is this. I want to add, before going in details, the other sensors that I need. I need to have light sensors, humidity, temperature of the external environment. I need to go to the soil to measure the dimensions, soil water potential, temperature, pH, NPK, plenty of sensors. Which is the work? The work is to do what is named sensor data fusion, because we don't need, my nirvana is to say, the impedance measure can tell you everything. This could be fantastic. With less than few euros, I will show you after in electronics term, I have everything. I'm sure that it will be not. So, one of the works that are in our hands as scientists, it is now to use as much as possible sensors for measuring what we can. And to apply, in this case, machine learning, artificial intelligence, to reduce the number of sensors, because low cost. So we need, now the work is to understand which are really the needed sensors depending on the application. So if the application, that will tell us, I need this sensor with the 10% of accuracy. Probably the accuracy is not needed, 1%. 10% is more than enough, but you have a low-cost sensor. So the work that we first are doing is exactly this, to understand what we need, the precision, the accuracy that we need. Because you can measure this, and now we see some details. This is the modulus, the phase, temperature, humidity of the air, ambient light, and moisture of the soil. Again, here we have a watering event. Which are these periodical changes? You see at the ambient light, you see at the temperature, are day and night. The plants go to sleep. During the night, or maybe they do something different. We see during winter, the impedance changes, and the changes in impedance are different, are smaller, because the plants during the winter, they go to sleep a little bit, they don't produce any more fruits. So, what is very good, and I was surprised when we started to do these studies, is that, yes, impedance is telling me a lot of things. I am sure I get the activity of the plant, clearly. And what was one of the, and now I go to show you some active projects. We did experiments, as you can imagine. Here we are in front of no more a tobacco plant. Here is an apple tree where we have our impedance sensors. We have our board, and here how I measure impedance. I don't use complex systems, low power, low cost. I use a relaxation oscillator. I put the plant in the loop of a relaxation oscillator. I know that I don't have to explain what it is. That's it. So with how much can cost a relaxation oscillator? Less than €1. So, fantastic. So with this information, I can have the measurement of one How I define it, the plant is breathing or beating a heartbeat. No, it's similar, no, to this information. So, thanks to this, we had once, it was one of the first, because, you know, when I received, well, okay, I can share it with you, I took the seeds from Israel coming to Torino. On the plants, I was deeply preoccupied to be blocked to with my seeds of tobacco seeds. I arrived in Torino, we planted a few plants. As you can imagine, the first months we were perfect killers of plants. They will die, most of them. After now, my guys are able to do a good job. But this was at the end the first information that we need to use water, less water, more water, and see what happens. We had once a strange plant. This strange plant had the impedance was increasing because the moisture was decreasing, the impedance increases because the soil is becoming drier, clearly, the impedance increases. We did not water it. In this case, this changes because we are not watering, but we had a huge decrease and after a huge increase of it. This plant, here we are talking of few days, when the plant started to change, few days in difference. And this plant, you look at this plant, was similar to the others, no different. Green leaves, healthy. After a few days, this plant died. This told me, you are on the right way. Because the plant, few days before dying, was telling me, I'm suffering, please help me. Because after I understood that this behavior, the agronomist told me, the plant opened all the possible channels for surviving. Like, you know, what happens to us, when you have difficulties to breathe, you try to open, to increase the efficiency of your breathing system, you know? The plant was doing exactly this, was opening as much as possible, but after a while, we did not recognize it, we did not do anything, and the plant died. So, also in this case is a very important information. And after having all this information, we had this, before we were talking of finance, of supporting helper. This was a regional project from Piedmont region. We call it Wapfruit. And in this project, we dig inside the soil at three different depths. 20, 40, and 60 centimeters. Because again, you just not need one depth, different depth, because the roots, they go down, and it's important that you measure more than one depth for having the right information. So we read the information, we transmit the information by LoRaWAN, then to the cloud for the algorithm, for taking the decision, for going to the pumps, and here we have a system for controlling the pumps for irrigation. This is a project, and I will show you the results in which we irrigated automatically, in this case, our crop. We developed. Nowadays, this is not the electronics I need. This was just a study to understand that we are able to do it. So I did not design, again, in terms of strategy of research. Don't start immediately to do the best circuit whenever. Do something that is useful and needed for understanding if it works. Because your ideas, sometimes they don't work. So you have to be sure that it works. And so from this type of study, you extract the information that you need to after design the low power, low cost, and blah, blah, blah solution. So, in this case, it's not the best. It's already low power. We already started, of course, to use everything low power as much as possible. In fact, these batteries are up and running from 2 years. and we did not have to change them. So by sure, we already started to apply some concept, but you know, the electronics are not the ones that I mentioned are useful. We have batteries. I don't want batteries in the future, so we have to continue to work, but we were able to extract our information using two sensors. This cost 300 euros, this cost a few euros. I put both because I want to be sure to have good numbers for understanding if I'm able to do something. But also in parallel, I put low cost to see, is this enough? If the answer is yes, I will never use this one. So, this is the way that we did for reaching our goals. And from the other side, another very simple circuit, in this case, by LoRa, we receive the information to open and close the pumps for irrigating our crop. So, what we did for taking the decision? We did with an expert in agronomy for irrigation, what they say the water retention curves, and from these curves they were able to extract the threshold from where you. And we had, in the first year, we did just a model for be sure for not destroying the crops of the farmers, because in this case we were in 3 different crops. Part of the crop managed by us, the rest of the crop was managed by the farmers, okay? In the first year, we said, okay, we mount everything, just we did not switch on the pumps. So we just did not open the pumps, but we had everything installed in the crop, and we had the first interesting information. First, you see here, blue and orange are how during the season, you see 22, and in Piedmont, 22 was the most dry region in Europe. So we had really huge problems of water. And this is the soil water potential. Well, you see, when you are in this area, you are in a good zone. So it means you are not watering too much, but you are not watering too less. What happened? Look at the orange and blue. In this period, the farmers watered too low, too small, because in this moment, probably the plants suffered. In this period, they watered too much because it's too much watered. And the green one, our thinking, our model, you say, of course, is a model. It stays, mathematically speaking, inside it. So, but we demonstrated that by our measurement, we were able to stay inside the thresholds. The black one is the curve for no watering. So it's a model to say, if I did not water, of course, here the crop will die, here the crop will die, here the crop will die. But okay, the farmers were good. Even after a bad season, they were able to have fruits. After 2023, we switched on everything. I was very preoccupied, of course, because from the model to the reality, the differences are huge, and this is the result of what we did. This is one of the 3, but all the others are similar. This is interesting mostly for September, and after I will tell you. But you see here, at the end of the season, we watered 50%. So we used half of the water. What is interesting is that in June, in July, you know, sorry, this is in Italian, but these are the part of the crop watered by the farmers. This is our part, watered part. So you see, we always watered less. In September, we watered much more. I asked to the farmers and the agronomist in this particular case, what happened? This particular type of tree of apples, the galaval, it is harvested in September. So the farmers, as usual, when they harvest, they stop watering. Why? Because in the past, September was not so hot. Probably also here, I don't know, but the last September was like August or July in Italy. It was very hot. So the farmers, business as usual, I harvest, I stop watering. But the soil was very, very dry. And in fact, our system decided to water. What the agronomist told me, and we are waiting for next year, here in these months, probably the crops suffered. So they suffered. So maybe, and this is a test that we will do this season, they told me, if you are lucky, let's say, hope we did a good job, these trees, your trees will be more productive because they did not suffer last year like the others. So we are very curious. And here I highlight you an important thing in agriculture. Because I presented this also in Torino, as you can imagine, and one guy from computer science told me, so I can do some measurements for days, 1 month, and there is a lot of results, a lot of data, and put down some artificial intelligence and decide which are the sensors used. I said, forget it. You need seasons, more than one season to understand what happened. I had to wait the next season to see if these trees will be less productive than mine. And this is why, from the other side, machine learning, big data, artificial intelligence is fundamental for agriculture. Because agriculture doesn't stream data in nanoseconds, milliseconds, but you have a huge amount of data because you have seasons of measurement and you need them all. So I don't want to say that we have to expect 3 years, 4 years for any results. We can start having good results, but forget to have very, very good results. You have to do seasons of studies for increasing the quality of what you're doing. Here, we just did it for 1 season, but now we have ideas to increase our system, also having this information. So consider to be patient, okay? Even if as scientists, we must publish, as we said. But we have the opportunity to publish because you can obtain, even now, some good results, but forget to think to have everything in a few months. So, talking about this, I want to say, I told you, I watered half. So you tell me probably you had half of the production, or your quality was not good. Our result was, the farmer used his irrigation, and because of a very dry season, at the end of the season, the farmers told me, I irrigated very much less than in the past, so imagine. But they watered too much again. We irrigated 50%, we obtained, for example, the diameter of our apples were 78 millimeters, and the good result is from 75 to 80. Perfect. And also, I don't want to say that we were better in quality, we were same quality because they measured the content of glucose inside, so how much was sweet, same a little bit more. Why? Because we put less water. So the apples were sweeter. So, wow. After this result, I tell you, I share with you, I did not expect a so great result. And I asked the farmer, the example I told you, go on place. Okay, I will not put to him this question if the result was bad. The result was fantastic. I said, how much will you pay for this system? He told me, tell me the price, I pay for it. So, low cost, yes, but when they see that it is effective, they are happy to pay for it, of course, but for sustainability, I cannot sell this system 50,000 euros, okay, as they miss the incomings, okay, so you have to do something that is balanced, but they also were very surprised. So, coming, because after time is passing and I have to do another thing, communication. With this paper in ISCAS in 2019, we demonstrated that the plant can be a wire. We transmitted 50 kilobits per second inside the plant. So, the plant is an ionic channel. There are ions coming back and down, up and down. There are two channels, xylem and phloem are the channels from which the plant takes nutrients from the soil and brings them up, and bringing from the leaves the product of the chlorophyll and photosynthesis, bringing them down. So it is possible to transmit an information. So we said, okay, so we can build an internet of plants. How? And we put two plants, tobacco, you see them, one in the same, of course, pot, and we put here on one plant the transmitter powered by solar cell, no batteries. And we put the receiver on the other plant powered by a plant microbial fuel cell. So two pieces of metal, a zinc mesh and a copper wire, producing tens of microwatts of power. With these two no batteries powering, I was able to transmit the impedance, because I put again, here I had my oscillator, you see here the frequency of the oscillator, but this is the frequency received here, not the ones transmitted here. So we were able to read the frequency of the oscillator of this plant on this side. And here we did the experience, we watered this plant. Again, I don't have to tell you, in this case the frequency decreases because the impedance is increasing, okay? But anyhow, we have what we need with this simple signal, and we were able to transmit it. We just published this in the new journal, and after I will mention you. And you see here, what I want to say is that we were able to transmit the impedance of this plant, but we did not do it, but you can do it. If you measure the attenuation of the signal you receive here in respect to the transmitted amplitude, you can have also the impedance of all the path from the first plant to the other. So you have in parallel the impedance of the plant itself and the impedance of the full path, having a single signal. So now, coming quickly to the end, by sure, when you have to transmit the information to the cloud, you can use several systems. Usually in a crop you have 0G, so don't think to use cellular signals. The best nowadays solution, in my opinion, is LoRa. Bluetooth is not so long range. LoRa, you can send the signals for kilometers with a good efficiency and very low power. So LoRa is nowadays the winner. Last but not least, artificial intelligence in agriculture is already used for robots, for controlling robots, for soil monitoring and crop monitoring. And I did not tell you, another thing is predictive analysis. If I do seasons of measurement and I see what happened, thanks to artificial intelligence, I can really elaborate a good amount of data, enough amount of data for previewing being in this situation now, maybe which will be the production of the future. So it is also very, very important and interesting. Here we are talking more, of course, of computer science. And last but not least, also blockchain, because, you know, the information that is transmitted, it is important and private. I want to be, but if you think to the full chain of value of the production up to the supermarket, from the crop to the supermarket, it is important that the end user, the buyer, has a good information, a trustable information. So robustness and trustability of information can be really helped by blockchain. And by the way, I go back, FAO. So you cannot imagine that FAO talks of blockchain. They did a specific publication for showing which can be the applications of blockchain to agriculture. For ending my presentation, I want to share with you, because I'm here representing CAS Society, the actions that we are doing. The first action, I set up, I can say I'm proud of it because I was the one who set up these new transactions. I had a fantastic support from all IEEE, so the transactions on agri-food electronics, because we have seen that in IEEE there were not possibilities. I raised up this journal because I didn't know where to publish in IEEE my work. I was publishing in Springer, in Elsevier. So guys from IEEE told me, Danilo, no, stop. Start publishing. So I said, so I must set up a journal. Yes, please do it. And so I said, what, me? Yes, okay, and I did. So with, of course, the help of others. And here, we are talking precision agriculture. I did not mention animals, livestock, of course. But I'm not working on it, so I didn't want to go into details, but it is so, and all the concepts that I already mentioned you. And as you can imagine, it is a journal application driven. So if you do, and I don't want to go to other fields, if you do a fantastic sensor for agriculture, IEEE sensor journal, because it's a sensor. If you do a perfect algorithm, or you have other, or you do, in this case, if you do use electronics system for solving problems and showing real applications in agriculture, this is your journal. And we already published 2 issues in last year, in 2023. We are, of course, now continuing. We were happy. We had about 60 submissions for the first year, is not bad. We were quite tough, so we had acceptance of 25%. So, but we wanted to start with quality, top quality, to start well the journal, and so we started this way. By sure, we linked the journal with conferences. We did a workshop in Quito last year, WAFE, the workshop on agri-food electronics, and in Torino I did last September the first edition of the CAFE conference, or CAFE, okay, conference on agri-food electronics, and the next year we already decided will be in Xanthi, Greece. In September we are deciding the dates, and after TAFE, WAFE, CAFE, and also I invented YAFE, because inside CAFE we had also industry for agri-food electronics. The vice president of the president of CAS Society told me, Danilo, stop. So acronym, okay, that's it. Don't go. Yeah, enough, okay? And so I stopped to inventing new. By the way, CAFE is not mine. It was Matias Miguez from Uruguay who invented CAFE, the name CAFE. Particularly, so I must give him your credit. So we have a special interest group in agri-food electronics. In this special interest group, you can be involved and be also not expert, but just to enter in the special interest group of CAS Society, but is open to everyone. We have agronomists, we have also people from other societies. You know very well the secretary, I'm sure. Me and the vice chair, Victor Greenberg will be the chair, and now, as always happens in societies in this group, Francois will become the vice chair, I will become the chair, and so we had enter another one for secretary. So you see, in fact, I'm here also because of the good friendship with Francois. We are working for creating the network. And it is not a spam place. We send you sometimes some messages. You can send maybe requests to the experts and enter in contact as one of the things that was mentioned in the previous talk, the previous roundtable, to enter in contact with experts, with people who can help you, or also to suggest new actions. Well, out of it, I hope that I was able to transfer you what I had in mind. I thank you so much, and in case, I guess that, do we have time for a few questions? I don't know. Let me know. I'm so late, so maybe people want to go to have lunch, so sorry, but Italians, we shake hands and we talk too much, okay? So, sorry for that. Thank you very much.
So thank you very much, Professor, for this nice presentation. I think we have time for a few questions. So,
Please.
You told us that currently your system is provided by graphic, but you think it would be useful to do energy harvesting, but which system or which kind of solution is the best for your application?
Great question, because you mentioned best. Best in engineering doesn't exist. So I take it's a perfect question, I thank you. Because always I mention optimal solutions. In fact, my answer is it doesn't exist the best. I mentioned LoRa, after I answer to your question, LoRa for transmission, because now really is we can say the best, but probably some guys I have a PhD with Vodafone. So communication guys are starting to understand that to enter in this field is important. So, answering to you, by sure, solar cells out of the soil are a very good solution. Now there are already, I saw fantastic works in flexible solar cells. So you can use in your flexible system also solar cells. They are becoming very efficient. So you can have a small, because again, you cannot put a solar cell like this in the plant. So you must put small, so this is why you must reduce as much as possible the consumption to reduce as much as possible the dimension. And solar cell, I have a work with, I can tell you because it's public, we also publish something. I work with ST Microelectronics in Catania, I have one of my PhD there now, because studying solar, the consumption of the production of a solar cell is proportional to the illumination. So you do a powering and a sensor in parallel. So you do two things. So in this case, but again, people are working on the triboelectric. So on the leaves. For example, if you put a sensor in a leaf, it can be fantastic to have a triboelectric production. So, but triboelectric are still very picowatts, so they are producing still less than is needed. But again, we trust the scientific community, by sure will increase. So again, application. So if I am on a trunk, maybe the solar cell is good. If I am on a leaf, the solar cell is not transparent. I don't know if they are producing transparent solar cell. In this case, could be good. In the soil, no solar cell. And so you have fuel cells that are taken, I did not mention, energy from the microbes. The microbial living system inside, it is reacting and producing electrons in contact with your metals. So, again, there are different ways, and it is a specific path of research to find low cost and simple, flexible, and we are also in a good way. So, thank you. And there are other maybe that I still don't know. But in principle, what I see now, the most used nowadays are the solar cells, effective solar cells and microbial and the fuel cells. This is why we use these two. But again, thank you.
Thank you.
Other questions? Maybe one there? No. Okay, yes, please.
Small question. How do you measure the soil water potential?
The soil water potential, I'm not an expert, I tell you something. You put ceramic membranes that enter in balance with the soil. So they are put in probably with a density, with a structure that is similar to what is the soil, and the content, the humidity, the content of water changes the epsilon r of the material, you know. So in this case are usually capacitance measurements. So changing the capacitance, the changing capacitance tells you how much this ceramic is able to enter in equilibrium with the fact you mount them and you leave them for weeks. Again, the timings in agriculture, nanoseconds, forget them. So maybe a few weeks after they enter in equilibrium with the soil, and the measurement of the capacitance tells you, in this case, of course, I'm not expert, I cannot tell you the physical reason, tells you how much the plant is able to get the water. So the efficiency, the effort that the plant, because it's related to a small soil water potential, means that the plant has to put a lot of effort for getting the water. Welcome. Okay, you said two. We
Any other question? So, if there is no other question, I think we will have a lunch.
Yes, bon appetit.
Thank you again.
Thank you.
Thank you again.